Welcome to Lecture 6. This week we're going to cover the topics of coordinates and basis, dimension of a vector space, change of basis, and row space, column space, and null space. We start by talking about coordinates and basis. A vector space is said to be finite dimensional if there is a finite dimensional set of vectors in V that spans V. And it's said to be infinite dimensional if it's not possible to find such a set. If it's not possible to find a finite set of vectors that spans the whole vector space. If we have a set of n vectors in a finite dimensional vector space, then this set S is called a basis for the vector space V if it satisfies two things. First of all, we need S to span the whole vector space. That means that we need the span of S to be equal to V. And the second thing we need is that we need S to be a linearly independent set. If these two rules are satisfied, then S is called a basis for V. And this is one of the important definitions in this course. Make sure that you learn this one. Recall from last week that the standard unit vectors, E1 is the vector with a 1 in the first position and all the other coordinates are 0. E2 has a 1 in the second position and all the other coordinates are 0, etc. Last week we saw that these span Rn. I actually only proved it for the case n equal to 3, that these vectors are linearly independent. If we have that we span the whole vector space, and if we have that they are linearly independent, then that means that they are a basis. This basis we call the standard basis for Rn. Anytime we have a base which is the most obvious one, we call it the standard basis for a vector space. So for example, the set S, which contains I, J, and K, as in the yellow box at the top, is called the standard basis for R3. For example, show that the set S, which contains the polynomials 1, x, x squared, x cubed, etc., all the way up to xn, is a basis for the vector space Pn, which is the polynomials of degree n or less. There's a typo here. This should be a hollow P. Now, we've done the work for this already. Last week, we showed that this set spans Pn. In other words, the span of S is equal to Pn. And last week, we saw that S is linearly independent. So we proved the two things we need to prove. So straight away, we can say, therefore, S is a basis for Pn. Now let's look at another basis for R3. Show that the vectors 1, 2, 1, 2, 9, 0, and 3, 3, 4 form a basis for R3. To answer this question, we need to prove two things. We need to prove that these three vectors are linearly independent, and we need to prove that they span R3. For the first one, if you recall, we talked about linear independence last week. To show that they are linearly independent, we need to show that the equation C1v1 plus C2v2 plus C3v3 equal to the 0 vector has only the trivial solution. In other words, the only solution of this equation is C1 equal to 0, C2 equal to 0, and C3 equal to 0. And for the second one, to show that they span R3, we need to show that C1v1 plus C2v2 plus C3v3 equal to B is consistent for every B. For any vector B, we need to be able to find C1, C2, and C3. And this is almost the same equation, except the first one has equal to 0 and the second one has equal to B. We've got two linear systems to consider. We need to show that the first one has only the trivial solution. We need to show that the second one is consistent for any B. These two linear systems have the same coefficient matrix, of course, because it's the same vectors. If I go back, first vector is 1, 2, 1. So the first column of our matrix is 1, 2, 1. Second column of our matrix is the second vector, and the third column of our matrix is the third vector. If we can show the determinant of A is not equal to 0, then we can prove both things at the same time. Why? Because if the determinant of A is not equal to 0, then that means A is an invertible matrix. So then AC equal to 0 becomes C is equal to A inverse of 0, and of course A inverse of 0. Multiply a matrix by a 0 vector, always get the 0 vector. So if A is invertible, then straight away we find that C is equal to 0. So the first linear system has only the trivial solution. And looking at the second equation, again, if A is an invertible matrix, we end up with C is equal to A inverse B. That means for any vector B, we can find C. So that means that the second linear system is consistent for any B. So to answer this question, all we need to do is calculate the determinant of A and show that this is not the number 0. But I'm going to leave that for you to do. You know how to calculate determinants now. I'm going to leave it for you to prove that the determinant of A is not equal to 0 because the determinant of A is equal to -1. So then we're finished. That proves that these vectors, v1, v2, and v3, form a basis for R3. The next example is titled the standard basis for R m by n or m and n, depending on which notation you want to use for the vector space of m by n matrices. But we're just going to look at it in the special case where m is 2 and n is 2. Show that the matrices 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1 form a basis for the vector space R2 by 2 of 2 by 2 matrices with real entries. So first we need to show that the only solution of C1 M1 plus C2 M2 plus C3 M3 plus C4 M4 equal to the 0 matrix, we need to show that the only solution is the trivial solution. But on the left, if we add these together, we just get this green matrix, C1, C2, C3, C4. How many solutions are there to C1, C2, C3, C4 equal to 0, 0, 0? Only the trivial solution. That proves that these four matrices are linearly independent. We also need to show that they span R2 by 2. Let B be any matrix in R2 by 2. We need to show that this linear system is consistent. We need to show that it's possible to find C1, C2, C3, and C4 such that C1 M1 plus C2 M2 plus C3 M3 plus C4 M4 is equal to B. But just like we did at the last on the last slide, if we add these four things together, we just get this green matrix C1, C2, C3, C4. And of course, if that's equal to the matrix A, B, C, D, then we know what values to put for C1, C2, C3, and C4. That means for any matrix capital B, we can find C1, C2, C3, and C4 such that this equation is true. This proves that these four matrices span R2 by 2. So we've done the two things we need to do. We've proved that this is a basis for R2 by 2. And this is called the standard basis for R2 by 2. Next example, show that the vector space P is infinite dimensional. Now, let me remind you, P is the vector space of all polynomials with real coefficients. All polynomials of any degree. Now recall, we say that a vector space is infinite dimensional if it does not have a finite spanning set. So we need to prove that. And we're going to start by supposing the opposite. Let's suppose there is a finite spanning set. Let's say we're going to call this S, and it's the polynomials P1, P2 up to PR. Now, one of these polynomials will be the polynomial with the biggest degree. Whatever it is, let's say n is the biggest degree of the polynomials in set S. That in turn means if we take any linear combinations of the polynomials in set S, then we would end up with a polynomial of degree at most n. But then that means there's no way to make the polynomial x to the power n plus 1 by using a linear combination of polynomials in S. And that contradicts the fact that these vectors in S need to span P. So therefore, there does not exist a finite set which spans P. Therefore, P is infinite dimensional. Here's some other infinite dimensional vector spaces. R to the power n, this means all of the sequences of real numbers. We looked at sequences of real numbers last semester in Mathematics 2. Capital F on the open interval from -infinity to infinity. This is the domain. This is the same as this real number here. Capital F on the domain from -infinity to infinity. That means the vector space of all functions defined on the real numbers. C, with domain from -infinity to infinity, is the vector space of all continuous functions defined on the real numbers, or to say it another way, with domain open interval from -infinity to infinity. C to the power k is all of the functions which are continuously differentiable k times. That means we can differentiate them k times, and every time we differentiate it, we have a continuous function. And C infinity is the vector space of all functions which we can differentiate infinitely many times. Now that we have the idea of a basis, we can start talking about coordinates relative to a basis. Let's suppose that capital S is a basis for a vector space V. Then that means two things. It means the vectors in S are linearly independent, and it means that span of S is equal to V. If the span of S is equal to V, that means any vector V can be written as a linear combination of the vectors in capital S. And if the vectors in S are linearly independent, that means we can do this in exactly one way. We're going to start talking about coordinates in a general vector space V. If S is a basis for vector space V, and that means that we can write V as a linear combination of V1, V2 up to Vn, then the numbers in this expression, in this linear combination, C1, C2 up to Cn, are called the coordinates of V relative to the basis S. If we write these coordinates in a vector, we would have a vector in Rn, and this is called the coordinate vector of V relative to the basis S, and it's denoted like this. Round bracket V, round bracket, subscript capital S is equal to, and then we have this row vector. Now, let me just remark that when we do coordinates, that means the order of the vectors in S is important. Some books use the term ordered basis. If you see ordered basis, that means a basis in which the order of the vectors in the basis is fixed. You can't change the order, they have to stay in the same order. Why? Because if you swap the positions of two vectors in a set, then the scalars in the linear combination would change, so you would get different coordinates. So let's assume that once we've got a basis, we have the vectors in a particular order, and that order stays fixed. So the idea is we're starting with some vector v in a vector space capital V, and then that's going to give us a coordinate vector in Rn. That's going to be a one-to-one correspondence. Let's do an example. Let's look at the vector space R3 with the standard basis I, J, and K. And we're going to be looking at the vector V, which has coordinate vector A, B, C. Then we could write V is equal to AI plus BJ plus CK. And that in turn implies that the coordinates of V relative to the basis S, we look at the number in front of I, that's the first one. We look at the number in front of B, that's the second one. And we look at the number in front of K, that's the third one, A, B, C. But that's exactly what we started with. Why is it exactly what we started with? Because we're using the standard basis. Find the coordinate vector for the polynomial Px equal to C0 plus C1x plus C2x squared plus dot 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 plus Cnxn relative to the standard basis for the vector space Pn. Well, recall that the standard basis is 1x, x squared, etc. up to xn. So what is the number in front of the 1? It's C0, right? C0 first. And then what is the number in front of the x? It's C1. So we write C1 and so on. The coordinates of the polynomial P relative to the basis S is the vector C0, C1, C2 up to Cn. Let's do another one. Find the coordinate vector of the matrix capital B is equal to ABCD relative to the standard basis for R2 by 2. So as we said earlier, capital B we can write as A multiplied by 1, 0, 0, 0 plus B multiplied by 0, 1, 0, 0, etc. We have scalars multiplied by the vectors in the standard basis. The first number is A, so that's the first coordinate. Second number is B, that's the second coordinate, and so on. The coordinates for capital B relative to the standard basis capital S is the vector A, B, C, D. Now let's make this a little bit more difficult. We showed in a previous example that these three vectors form a basis for R3. Part 1, find the coordinate vector of the vector 5, -1, 9 relative to the basis capital S containing these three vectors. And then question 2, find the vector u in R3 whose coordinate vector relative to S is -1, 3, 2. Okay, let's answer question 1 first. We want to find the coordinate vector of 5, -1, 9. So in other words, we want to find the numbers C1, C2, and C3 such that V is C1, V1 plus C2, V2 plus C3, V3. In other words, if we put the numbers in, we want to find the numbers C1, C2, and C3 in the equation. 5 -1, 9 is C1, 121, plus C2, 290, plus C3, 334. So that means we need to solve a linear system. Look at the first position first of all. 1C1 plus C2, 2C2 plus 3C3 is equal to 5. And then second position, 2C1 plus 9C2 plus 3C3 is equal to -1. And then looking at just the third positions, 1C1 plus 0C2 plus 4C3 is equal to 9. But of course, you know how to solve linear systems like this, so I'll just tell you the answer. The solution to this linear system is C1 is 1, C2 is -1, and C3 is 2. So therefore, the answer to this question is the coordinates of the vector V relative to the basis S is 1, -1, 2. Question 2 was one which goes in the opposite direction. We're told the coordinate vector relative to S is -1, 3, 2, and we want to find the actual vector U. And it's easier to go this way. Why? Because -1, 3, 2 means that the vector U that we want is -1 V1 plus 3 V2 plus 2 V3. So all we're going to do is we're going to take the vectors for V1, V2, V3, put them in here and simplify it. And I will leave it for you to check that if I haven't made any mistakes, the answer is 11, 31, 7. Next idea, the idea of dimension. We've seen two bases for R3. We've seen I, J, and K, and we've seen V1, V2, and V3. How many vectors are in each of these bases? Well, in the first basis, the standard basis, we can count them, 1, 2, 3. And in this other basis that we've been looking at, again, we count them, 1, 2, 3. Each basis had 3 vectors in. And in fact, this is a rule. All bases for a finite dimensional vector space have the same number of vectors. Any basis for R3, for example, always has 3 vectors in it. And that number is important. We call that number the dimension of V, if V is a finite dimensional vector space. The dimension of a finite dimensional vector space V, which we call dim of V, is the number of vectors in a basis for V. And just so that we make things consistent, we say that the dimension of the zero vector space is 0. Now, just before I go on, engineers often like to use a different word for this. Engineers often use the term degrees of freedom instead of dimension. I'm going to be using dimension in this course. Let V be an n-dimensional vector space. That means every basis for V contains n vectors. And let the set containing V1 up to Vn be any basis for V. If a set in V has more than n vectors, then it's linearly dependent. If a set in V has fewer than n vectors, then it does not span V. So, for example, the dimension of Rn is equal to n. Why? Because we know that the standard basis for Rn has n vectors in it. So every basis for Rn also contains n vectors. The dimension of Pn is actually n plus 1. For example, recall that the standard basis for Pn is 1, x squared up to xn. And if we count the number of vectors in this standard basis, 1, 2, 3, etc., we would end up with n plus 1 vectors. And the dimension of R2 by 2 is equal to 4, because the standard basis contains the following 4 vectors. That's another reason why R2 by 2 is a very nice notation for the set of 2 by 2 vectors. We can easily see 2 by 2 is the same as 4. Similarly, the dimension of Rm by n is m multiplied by n. Let's suppose we have a set S containing R vectors. Then that means every vector in S is expressible as a linear combination of the vectors in S. And if the vectors in S are linearly independent, then they automatically form a basis for the span of S. So we can conclude from this that the dimension of the span of R linearly independent vectors is equal to R. In other words, the dimension of the space spanned by a linearly independent set of vectors is equal to the number of vectors in that set. Next, let's look at the dimension of a solution space. Find a basis for and the dimension of the solution space of the following homogeneous linear system. Now, you know how to solve this. I'm just going to tell you the solution of this homogeneous linear system is this. x2, x4, and x5 are 3 variables. x1, x3, and x6 are given by equations. Now, we can write this in a different way. We can write this as a vector. x1, x2, x3, x4, x5, x6 is minus 3x2 minus 4x4 minus 2x5, because x1 is this. x2 is 3, so just write x2. x3 is equal to minus 2x4. x4 is 3, so just write x4. x5 is 3, just write that there, and then 0. And we can write this as x2 multiplied by the vector minus 3, 1, quadruple 0, plus x4 multiplied by the vector minus 4, 0, minus 2, 1, double 0, plus x5 multiplied by minus 2, triple 0, 1, 0. In other words, every solution of the linear system can be written as a linear combination of these three vectors. So that means that these vectors span the solution space. I'm going to leave it for you to check that these three vectors are linearly independent. That means that these three vectors form a basis for the solution space. And from that, we can say the solution space has dimension 3. There's 3 vectors in the basis for the solution space, so the dimension of the solution space must be 3. Let's talk about some more theorems. First of all, let V be an n-dimensional vector space, and let capital S be a set in V with exactly n vectors. Then the following 3 conditions are equivalent. S is a basis for V, S spans V, and S is linearly independent. What that means is, if you know that S spans V, then you don't also need to prove that S is linearly independent. You get that S is linearly independent free of charge. Or if you know that you have n linearly independent vectors in an n-dimensional vector space, you don't also have to prove that S spans V, because you get S spans V free of charge. You only need to prove one of these, and you get the other one straight away. So, for example, explain why the vectors minus 3, 7 and 5, 5 form a basis for R2, and part B, explain why the vectors 2, 0, minus 1, 4, 0, 7 and minus 1, 1, 4 form a basis for R3. Part A, first of all, neither vector is a scalar multiple of the other one. So that means they're linearly independent. But by the last theorem, if we have a linearly independent set of 2 vectors in Rn, then immediately we know that they form a basis. We don't also need to prove that they span R2. We get that free of charge. Now let's look at B. First of all, let's just look at V1 and V2 in 3. Both of these vectors have second coordinate 0, so both of these are in the x, z plane, and these 2 vectors are not a multiple of each other. So these 2 vectors are linearly independent from each other. So therefore, they must form a linearly independent set in the x, z plane. Vector V3 does not have a 0 in its second position, it has a 1. So V3 is not in the x, z plane. So that tells us that the set of vectors V1, V2, V3 is linearly independent. Because R3 is 3-dimensional, and because we have a linearly independent set of 3 vectors in R3, straight away we know it's a basis for R3. We don't need to prove that it spans R3, we get that free of charge. It's enough to show that it's linearly independent. Let S be a finite set of vectors in a finite dimensional vector space V. If S spans V, but is not a basis of V, then that means S has too many vectors. What we can do is we can remove some vectors from S, and we can obtain a basis for V. Part 2, if S is a linearly independent set, which is not already a basis, that means it's linearly independent, but it doesn't have enough vectors in it, then we can enlarge it to a basis for V by putting extra vectors into it, putting the correct extra vectors into it. This part 2 is an idea which we will come back to in the last lecture. In lecture 12, we're going to need this idea. But for now, let's move to the next figure. If W is a subspace of a finite dimensional vector space V, then we know 3 things. W must also be finite dimensional. If V is finite dimensional, if W is contained inside V, then W must be somehow smaller, or at least not bigger than V. So if V is finite dimensional, the smallest one must also be finite dimensional. The dimension of W must be less than or equal to the dimension of V for the same reason, and the only way that they can be equal is if they have the same dimension. Or to say that another way, the only way that we can have the dimension of W is the same as the dimension of V is if W is equal to V. Let's move on. My third idea for this week's lesson is the idea of change of basis. Let's suppose we have the vector space R2, and let's suppose we have 2 bases for V. And let's suppose they look like this. I want to express the vector x in terms of b1 and b2, and I want to express the vector x in terms of c1 and c2. If I draw grid lines like this, then it's going to be easy to see how we do this. Looking at the left picture, first of all, how many b1s and how many b2s do we need to get from the origin to x? And the answer is, if we do 3b1 first, and then we do plus b2, then we move from the origin to x. So x is 3b1 plus b2. That means the coordinates for x relative to the basis b are 3, 1. And there's another way I could write this. Instead of a column vector, instead of a row vector, maybe I want to write that as a column vector. The coordinates for x relative to the basis b, I could also write as square bracket x, square bracket b, 3, 1. We need 3b1 plus 1b2. Now let's look at the right-hand picture and let's do the same thing. How many C1s and how many C2s do we need to go from the origin to x? I need 6C1 plus 4C2 to get from the origin to the vector x. So x is 6C1 plus 4C2. The coordinates of x relative to the basis c are 6, 4. And there's 2 different ways to write this, depending on if we want a row vector or if we want a column vector. The key idea for this section is, how do we go from the coordinates for x relative to the basis b to the coordinates for x relative to the basis c? How do we change the coordinates relative to one basis into the coordinates relative to the other basis. For example, suppose that we hadn't already done the picture. Let's suppose that we have two bases for a vector space V. Suppose we know that B1 is 4C1 plus C2, and we know that B2 is minus 6C1 plus C2. And finally, suppose that we know that the vector x has coordinates relative to the basis B equal to 3, 1. Find the coordinates for x relative to C. Well, we have actually already done this, so we actually know what the answer is going to be, but let's pretend that we don't know that yet. Pretend that we don't know that the answer is going to be 6, 4. So what can we do? We're starting with the information that the coordinates for x relative to the basis B is 3, 1. That means x is 3b1 plus b2. And what we want to calculate is the coordinates for x relative to the basis C. In other words, we want the coordinates of 3b1 plus b2 relative to the basis C. But everything is linear. This is a course called about linear algebra. So that's the same as 3 times the coordinates of b1 relative to C plus the coordinates for b2 relative to C. Or I could write this as a matrix multiplied by a vector. That's the matrix where the first column is the coordinates for b1 relative to C, and the second column is the coordinates for b2 relative to C, and then multiplied by 3, 1, which of course is what we started with. So to answer this question, we need to know what are the coordinates for b1 relative to C, and what are the coordinates for b2 relative to C. But the question told us this. The question told us that b1 is 4c1 plus c2, and b2 is minus 6c1 plus c2. So just from that information, straight away we can write down that the coordinates for b1 relative to C is 4, 1, 4 and 1. And the coordinates for b2 relative to C, look at the numbers, we have a minus 6 and we have a 1, so minus 6, 1. So we have all the information we need. That means the coordinates for x relative to the basis C is the matrix, first column 4, 1, second column minus 6, 1, multiplied by the vector 3, 1, and that gives the answer 6, 4, which of course is what we were expecting the answer to be. Now, what we've done here is the coordinates for x relative to C is a matrix 4 minus 6, 1, 1 multiplied by the coordinates for x relative to the basis B. In this section, it's going to be about finding this matrix. Let's write down this theory as a theorem. Let's suppose B and C are two bases for a vector space V. And because each one of these has n vectors in, that means that the vector space V is an n-dimensional vector space. The theorem says then there is a unique n by n matrix, which is called P, and then underneath P, C arrow from B, such that the coordinates for x relative to C is this matrix P multiplied by the coordinates for x relative to B. And the theorem tells us how to find this matrix P. The columns are just the c-coordinate vectors of the vectors in the basis B. So in other words, P, arrow from B to C, or if you prefer, arrow C from B, is the matrix where the first column is the coordinates of B1 relative to C, the second column is the coordinates of B2 relative to C, etc. Now it's easy to get confused because we have two bases here. So remember that the basis the arrow points towards is the one that appears just here, and the basis that the arrow goes away from is the one that we put inside the square brackets. As long as you remember which way round we're doing B and C, then you can do this. Just a warning before we go on, if you're looking in other books or you're looking online, different books use different notation here. Your textbook, so the notation I'm going to be using, uses a notation where C is on the left and B is on the right, and then the arrow points from B to C. But other books you might be looking in have B on the left and C on the right, but again, the arrow points from B to C. It doesn't really matter if you put B on the left or B on the right, as all that matters is which way the arrow points. We're going from B to C. This matrix, P, arrow pointing from B to C, is called the change of coordinates matrix from B to C, or it's also called the transition matrix from B to C. Arrow points from B to C, so this is from B to C. Anytime you're given a question, for an example, exam question which says from B to C, then you know which way to draw your arrow. This matrix, this change of coordinates matrix, is invertible, and it has the property that if we take its inverse, we also get a change of coordinates matrix, but we get it with the arrow going the other way. The opposite of going from B to C is going from C to B. And that's a good place for me to take a break. Let's take a 10-minute break and let's continue at, let's say, 2 minutes past 3. And now let's continue. Let's suppose our vector space V is R2 and we have two bases, B and C. And we're told that B1 is the vector minus 9, 1. B2 is the vector minus 5, minus 1. Vector C1 is 1, minus 4. And vector C2 is 3, minus 5. And we're asked to find the change of coordinates matrix from B to C. And we have a theorem which is going to help us do this. The augmented matrix with columns C1, C2, B1, B2 is row equivalent to the augmented matrix where I is on the left and P from B to C is on the right. So if you use the notation in your book with a leftwards pointing arrow, remember that C on the left goes to C on the left, and B on the right goes to B on the right. So this is what we're going to do. We're going to start with this augmented matrix. We would row reduce it, and then we're going to find the change of coordinates matrix from B to C. So we're going to start with the augmented matrix, first column C1, second column C2, third column B1, fourth column B2, and then we're going to row reduce this. And I'll leave this calculation for you to check. This is row equivalent to 1064, 01, minus 5, minus 3. So that's the identity matrix on the left, and then a 2 by 2 matrix on the right. And it's this 2 by 2 matrix on the right which we want, because the 2 by 2 matrix on the right is the change of coordinates matrix from B to C. So the answer to this question is the change of coordinates matrix P from B to C is the matrix 6, 4, minus 5, minus 3. Let's do another one. Let's suppose we have two bases for R2 and we're given each of these four vectors. Find the change of coordinates matrix from C to B and find the change of coordinates matrix from B to C. Now, in the first step, we need to find the change of coordinates matrix from C to B. So that's the opposite way from what we did before. Before we were going from B to C, but now we're going from C to B. Now, here, B is on the left and C is on the right. So we're going to start with the augmented matrix where B is on the left and C is on the right. And then we're going to row reduce this. I'll leave that for you. Check that this augmented matrix is row equivalent to 1053, 0164. That's the identity matrix on the left, and then on the right we have the 2 by 2 matrix 5364, and that's the one we want. The answer is the change of coordinate matrix from C to B is the 2 by 2 matrix 5364. And then in part 2, we wanted the other change of coordinates matrix. We wanted the change of coordinates matrix from B to C. But that's just the inverse of the matrix that we found. So we want the inverse of the matrix 5, 3, 6, 4. And an inverse of a 2 by 2 matrix is easy. I'll leave it for you to check that we get 2 minus 3 over 2 minus 3, 5 over 2. Let's look at some past exam questions. This is the final exam from the 30th of December 2019. Question 3 said, let A and B be two bases for a vector space V, a three-dimensional vector space, and we're told the way that these are related. We're told that A1 is 4B1 minus B2, and we're told that A2 is minus B1 plus B2 plus B3, and we're told that A3 is B2 minus 2B3. And then in part A, we're asked to find the change of coordinates matrix from A to B. Now, let's look at the first relation that we're given. We're told that A1 is 4B1 minus B2. So in other words, straight away we know that the coordinates for A1 relative to the basis B, 4 minus 1, 0. And then we're also told that A2 is minus B1 plus B2 plus B3. The numbers are minus 1 plus 1 plus 1 here. So straight away we can write down that the coordinates for A2 relative to the basis B are minus 1, 1, 1. And for the same reason, we can see that the coordinates for A3 relative to the basis B are 0, 1, minus 2. We haven't done anything difficult yet. We've just looked at the information we've been given. And then, as we've seen earlier, the change of coordinates matrix we want is just the matrix where these are its columns. First column 4, minus 1, 0. Second column minus 1, 1, 1. And third column 0, 1, minus 2. And that's it. That's pretty much all we need to do. Just write a few sentences to explain what you're doing, and that's the answer to part A. Part B, find the coordinates for x relative to the basis B for the vector x, which is 3a1 plus 4a2 plus a3. So basically what we're told is the coordinates for x relative to the basis A, the numbers here are 3, 4, and 1, and we're asked to calculate the coordinates for x relative to the basis B. So really all we need to do is to multiply our matrix that we found in part A by this vector. And that's it. That's 25 points from a final exam, a quarter of a final exam. Let's look at another exam. This is the second midterm exam from the 5th of December 2018. And this is a different type of change of coordinates question. This time we have two bases, call them V and W, and this time we're not told how they're related, but we're told they're vectors. We're told that V has the vectors minus 1, 1, 0, 2, minus 3, minus 3, and 1, minus 3, minus 5, and we're told that W is the basis containing the vectors 1, 2, 4, 1, 2, 3, and 2, 3, 6. Part A, find the coordinates of this vector V relative to the basis V. So what we want to do is we want to find the numbers C1, C2, and C3, which make V be equal to C1 multiplied by minus 1, 1, 0, plus C2 multiplied by 2, minus 3, minus 3, plus C3 multiplied by 1, minus 3, minus 5. So we have to solve a linear system. And after we find the linear system, we find that C1 is 2, C2 is 3, and C3 is minus 2. So the answer to this part of this question is the coordinates of v relative to the vector v are 2, 3, minus 2. And then the question went on with part B. Find the change of coordinates matrix from V to W. So the idea is we're going to start with the augmented matrix with W on the left and V on the right, and then row reduce it so we end up with the identity matrix I on the left, and then the change of coordinates matrix on the right. So here we go. We start with the vectors in W on the left and the vectors in V on the right. Row reduce it until we end up with the identity matrix on the left and the matrix that we want on the right. So it's similar to the examples we were doing. And then part C of this question said, find the coordinates of the vector V that we've had before relative to W by using the change of coordinates matrix. We know the coordinates of V relative to V. We know the change of coordinates matrix from V to W. We want the coordinates of V relative to W. So we do matrix multiplied by vector and we get the answer. Now, of these two questions, I think that the 2019 question was easier than the 2018 question. But I remember that in 2019, the marks that we gave to students were much lower than we gave in 2018. And the only reason I can think is the students in 2019 only studied the previous year's exam. They knew how to solve the type of question which was asked 1 year earlier, but they didn't know how to solve the other type of question. And I think this is an example that you need to study the whole course. You need to study all of the theory in the course, not just the questions which were asked the previous year, because we might give you an easier question, but which is asked in a different way. And if you only studied the previous year's exam, then you don't know how to solve that year's easier question. Or perhaps you disagree with me. Perhaps you think that 2018 question was the easier one. Anyway, I was deliberately quick there. You can find past exam papers in OLearn and you can read these solutions yourself. Our final idea for this week's lesson is about row space, column space, and null space. Consider an M by N matrix. The row vectors of A are this. The entries in the first row of A, if we write this as a row vector, we call this R1. If we take the entries in the second row of A and write in a row vector, we call that R2, and so on. These are called the row vectors of A. Now know that each row vector is in Rn for an M by N matrix. And note that there are M row vectors because A has M rows. And similarly, the column vectors of A are these vectors. The first column, the second column, and so on of A. Each one of these column vectors is an Rm, and there are n column vectors because A has n columns. For example, find the row and column vectors of this 2 by 3 matrix. The row vectors are R1 is, oh, there's a typo here. R1 is 2, 1, 0, and R2 is 3, minus 1, 4. And the column vectors, there's another typo here. Small c1 is 2, 3, small c2 is 1, minus 1, and small c3 is 0, 4. So let A be an n-by-n matrix. The subspace of Rn, which is spanned by the row vectors of A, is called the row space of A. And we denote this as row A. The subspace of Rm, which is spanned by the column vectors of A, is called the column space of A, and this is denoted by col A. And then finally, the null space of A is this subspace. It's the set of all vectors in Rn which satisfy that Ax is equal to the 0 vector. This is a subspace of Rn. Now consider the linear system Ax equal to B, and note that Ax is the same as a linear combination of its column vectors. It's x1 multiplied by c1 plus x2 multiplied by c2 and so on. So that means Ax equal to B is consistent if and only if B is a linear combination of the column vectors of A. That's an important idea. Let's write that as a theorem. The linear system Ax equal to B is consistent if and only if B is in the column space of A. Let's do an example. Let's look at this linear system. Show that B is in the column space of A by expressing it as a linear combination of the column vectors of A. If we solve this linear system by Gaussian elimination, and you can check this, we find that the solution is x1 is 2, x2 is minus 1, and x3 is 3. So that means that this vector B, 1 minus 9 minus 3, is equal to 2 times the first column minus 1 times the second column plus 3 times the third column of A. Let A be this 3 by 4 matrix, let U be this vector in R4, and let V be this vector in R3. 4 questions. Is U in the null space of A? Is U in the column space of A? Is V in the null space of A? Is V in the column space of A? Question 1, first of all. Let me remind you that the null space of A is the set of vectors x in R4 which satisfy that Ax is equal to 0. This is a subspace of R4 because A is a 3 by 4 matrix. So that means a vector U is in the null space of A if and only if we have that AU is equal to 0. So what we're going to do is we're going to calculate AU. We're going to do matrix multiplied by vector, and we're going to see, do we get the 0 vector? And I'll leave it for you to check that yes, A multiplied by U is equal to the 0 vector. So the answer is yes. This vector U is in the null space of A. Question 2, is U in the column space of A? Now, because A is a 3x4 matrix, the column space is a subspace of R3. But U is in R4, so straight away the answer is no. U is not in the column space of A. Is V in the null space of A? No, because V is in R3, but the null space of A is a subspace of R4. And then finally, is the vector V in the column space of A? To be able to answer this, we need to reduce the augmented matrix AV to row echelon form. So let's start with this augmented matrix, a 3x5 matrix, and then I'm going to ask you to check that this is row equivalent to this matrix. So is this linear system consistent? And the answer is yes. There is not a pivot in the right-hand column. The right-hand column does not contain a pivot. Therefore, this linear system is consistent. So the answer to this question is yes. V is in the column space of A. Theorem. Suppose that AX equal to B is consistent. Let's suppose X is any solution of AX equal to B, and let's suppose that S is a basis for the null space of A. Then every solution of AX equal to B can be written in this form. X0, that's the solution we've already found, plus a C1v1 plus C2v2 plus dot 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 plus CKvk. That's a linear combination of the vectors in the basis for the null space of A. Conversely, the vector x in this formula is a solution of AX equal to B for any choice of scalars Cj. So let's just talk about this briefly. We have this, we're writing our solution like this. We have x0 plus C1v1 plus C2v2 plus dot 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 plus CKvk. So we have a particular solution, or one solution of AX equal to B, and then we get to add on a linear combination of the vectors in the null space. Or in other words, we're going to add on the general solution of AX equal to B, and altogether we get the general solution of AX equal to B. That's a particular solution of AX equal to B plus the general solution of the homogeneous system AX equal to 0, and that gives us the general solution of AX equal to B. This is an idea we're going to be using again in Mathematics 4 when we study differential equations. Let's talk about bases for row spaces, column spaces, and null spaces. First of all, two important theorems. Elementary row operations do not change the null space of a matrix, and elementary row operations do not change the row space of a matrix. Now notice that we've had three spaces here, row space, column space, and null space, but I only have two theorems. That's because elementary row operations can change the column space of a matrix, so be careful there. For example, consider A and B. Now note that A and B are row equivalent. The column space of A is the span of the vector 1, 2, because the second column of A is just 3 times the first column of A. And the column space of B is the span of the vector 1, 0, but that's not the same as the column space of A. So be careful. Elementary row operations do not change null space, they do not change row space, but they can change column space. Find a basis for the null space of this 4 by 6 matrix. We need to find the solution space of AX equal to 0. And I leave it for you to check that these two matrices are row equivalent. We're using the fact that row operations do not change a null space. They do not change AX equal to the solutions of AX equal to 0. So what we can do is we can just look at the solution space of the right-hand augmented matrix. We can write down its solution, or I don't want it like this. I want it in terms of vectors. I can write this as x2 multiplied by a vector plus x4 multiplied by a vector plus x5 multiplied by a vector. And it's these three vectors that we want. These three vectors are linearly independent. Straight away we can see this is a 1, a 0, and 0. So the first vector is not a linear combination of the second two. Likewise, if we look at the fourth position, a 0, a 1, and a 0, the second vector is not a linear combination of the first and third vectors. And looking at the fifth position, the 0, 0, and 1. So the third vector is not a linear combination of the first. These three vectors give us a basis for the null space of A. Now, in the previous example, first I found the solution of AX equal to 0. Now, what we could do is we've got three variables, x2, x4, and x5. We can set the first one to be 0 and the other two to be 0. And then what do we get? Then we get -3, 1, 0, 0, 0, 0. And that gives us the first vector in the null space of A. Or we could choose another one of these to be 1. Let's say x4 is 1, and put x2 is 0, x5 is 0. That would give us the second vector in the null space of A, and so on. Suppose that a matrix R is in row echelon form, REF. Then the row vectors with the pivots, so that means the non-zero vectors, form a basis for the row space of R, and the column vectors with the pivots, by which I mean the pivot columns, form a basis for the column space of R. So, for example, find bases for the row and column spaces of this matrix R, which is in REF. We use the previous theorem. We're going to look where are the pivots, and I've drawn them here in green. There's a pivot in the first row, there's a pivot in the second row, and there's a pivot in the third row. So that tells us that R1, R2, R3 is a basis for the row space. Which columns have pivots in? There's a column in the first column. There's a pivot in the first column, there's a pivot in the second column, and there's a pivot in the fourth column. So that tells us that C1, C2, C4 gives us a basis for the column space of R. So if we're in REF, if we're in row echelon form, then that's straightforward. Find a basis for the row space of this matrix. And the key idea here is that elementary row operations do not change the row space of a matrix. So we can row reduce this to get to REF. And then step 2, we're going to take the row vectors of R which contain a pivot. As always, I'm going to ask you to check my calculations. Please check that A is row equivalent to R. R has pivots in its first, second, and third rows. So these are the vectors that we want. R1, R2, and R3, the first 3 rows of capital R, give us a basis for the row space of A, which is the same as the row space of R. But as I said earlier, elementary row operations can change the column space of a matrix A. So what do? How can we find a basis for the column space of A? The key point is that even though they can change the column space, they do not change which columns of A we want in our basis. Theorem: the pivot columns of A form a basis for the column space of A. So our method is this. Step 1, we're going to reduce our matrix A to REF, and we're going to call this new matrix capital R. We're going to find the pivot columns of capital R, and then we're going to go back to the original matrix A, and we're going to take the same columns of A, the pivot columns of A. If we take the pivot columns of R, we might get the wrong answer. We don't want that. We want the pivot columns of A. So for example, find a basis for the column space of this matrix. It's the same one we just looked at. So step 1, row reduce it. Here it is. Look at R. Where are the pivot columns? The pivots are in the first, third, and fifth columns of R. So the pivot columns of R are the first, third, and fifth columns. That means that we want the first, third, and fifth columns of the matrix A that we started with. So first column of A and third column of A and fifth column of A give us our basis for the column space of A. And one more example for today's lesson. Find a subset of these 5 vectors that forms a basis for the span of these 5 vectors. Now we're in R4, and span of V1 up to V5 is going to be a subspace of R4. So it's going to have at most dimension 4, perhaps dimension less than 4. So straight away we know we have too many vectors. At least one of these we're going to be wanting to throw away. Now, if we write these vectors as columns of a matrix, then instead of looking at the span of V1 up to V5, we can instead just look at the column space of A. The span of these 5 vectors, if we think of them as column vectors, is the same as the column space of A, because the column space of A is the span of the column vectors of a matrix. So we do what we did before. We're going to row reduce capital A. We're going to look to see where are the pivot positions, which are the pivot columns, and then we're going to go back to A and we're going to choose those columns. Check this for me. Check that A is row equivalent to this matrix. This matrix has pivot columns in the first, second, and fourth columns. So we want the first, second, and fourth columns of A. In other words, the A set containing V1, V2, and V4 is a basis for the span of V1 up to V5. And that is the end of this week's lesson. Next week, we're going to talk about rank and nullity, the fundamental matrix spaces, linear transformations, composition and inverse transformations, and isomorphisms. Are there any questions?